All right, welcome to Math466 Advanced Applied Analysis. This is lecture 3. And so what we're going to do today is we're going to continue our work with the exponential function. We're going to talk a little bit about LP spaces, why we care about them, and then we're going to start doing some of the properties of Fourier coefficients. So to start with, let's see, it's not turning. No, it's not. It's one of those days. All right, we'll start over here. So En of x we define to be as e to the 2 pi I n x. And what's nice about this is every time I increase x by 1, I return to where I started. And you can write this out as cosine of 2 pi nx plus I sine 2 pi nx. And we've talked about how you can write cosines and sines in terms of sums and differences of the exponential function. We will typically work usually on 0, 1, sometimes minus a half to a half. So the minus a half to a half is convenient if the action is happening at 0, because if it's happening at 0, then going in one direction you go into the positives, and going in the other direction you go around to 0.99999. And so in those situations, if our function is periodic, we'll just look at negative 1/2 instead. For the function to be periodic, we want f of 0 to equal f of 1, or f of 1/2 to equal f of negative 1/2. So f is periodic with period 1 if f of x plus 1 equals f of x. And we've talked about an inner product. So the inner product of f and g is defined to be the integral from 0 to 1 of f of x, g of x bar dx. And of course, we don't have to look at the interval 0, 1. We could look at other intervals as well. For most of what we're going to do, we will spend most of our time on 0, 1, at least in the beginning of the semester. We're looking at functions that are periodic with period 1, so you can reduce to the unit interval. What's the danger if we're looking at the real line? So we're looking at now not 0, 1, but minus infinity to infinity. What do we now have to be very careful about? So there's no overlap between this and my previous class, so this was a warning I gave everybody. So if we go from minus infinity to infinity, we've now introduced an infinity. And now you have to worry, does the integral converge? You still have to worry about the integral converging here. Just because it's on 0, 1 doesn't mean, oh, I don't have to worry about convergence. But convergence is now much easier to obtain. If the function is continuous, for instance, that's enough to ensure convergence. If I'm now on minus infinity to infinity, I now need decay. And so what we'll often do is we'll look at what's called an LP space of, say, AB is going to be the set of all functions f such that the integral from a to b of f of x to the pth power is less than infinity. And then the norm we will introduce is the pth norm will be the integral from a to b of f of x to the p dx to the 1 over p. Okay, so now that we have these definitions, we can start looking at these various LP spaces. We can start looking at the various integrals and see what we get. Okay, so example. Let's look at LP of 0, 1. So the most important p's are 1, 2, and infinity. And infinity basically just means the sup norm. I'm not going to get into that too much right now. And how many of you have done measure theory? Okay, I'll use the subjunctive. If you were to have done measure theory, you would have seen that there's a nice relationship between sums of reciprocals of exponents. And one of the reasons 2 is so nice is that 1/2, the formula you get for the reciprocals is 1 over p plus 1 over q equals 1. And so if I give you a P, the corresponding Q, the complementary Q, satisfies this. And if P equals 2, Q equals 2, so you stay in the same space. This is one of the reasons why square integrable functions is so nice. There's a great theorem lurking in measure theory. So we can study things on 0, 1. If I tell you a function is integrable, is it square integrable? So f is in L1 of 0, 1. Is f in L2 of 0, 1? You always want to get a sense of how strong is a condition. So if I tell you that my function is absolutely integrable, must its square be integrable? 50-50 chance. Or at least does it sometimes work? So yes, can somebody give me an example where it works? What kind of functions, if they are integrable, will they be square integrable? Polynomials. In fact, bound functions, continuous functions. So there's a large class of functions which, if the absolute value has a finite integral, then the absolute value squared will have a finite integral. And so bounded is more than enough. So if we're going to find a counterexample, we need to search for unbounded functions. That's the only chance we have. So can you give me an unbounded function that's integrable on 0, 1? So it's got to blow up, and it can't blow up too badly because it has to be integrable. So what's your go-to example of a function that blows up? 1 over x. Okay, is 1 over x integrable? Can I integrate 1 over x from 0 to 1? So this would be the limit as epsilon goes to 0 of the integral from epsilon to 1 of 1 over x. This is the limit as epsilon goes to 0 of the natural log of x evaluated at 1 and epsilon. Natural log of 1 is 0. So I get this is equal to negative limit as epsilon goes to 0 of the natural log of epsilon. If you want, this is the limit as epsilon goes to 0 of the log of 1 over epsilon. And you can see, oh, well, if epsilon is going to 0, 1 over epsilon is going to infinity. This goes to infinity. We've just found a function which is not integrable. That should be our square. So if I want to find a function whose square is not integrable, here we go. So I want a function that squares to 1 over x. What function squares to 1 over x? So it would just be 1 over square root of x. Or more generally, we could take f of x equals x to the negative r. And what range do we want for r? It's got to be integrable, so we want r to be less than 1, because we want it to be integrable. If r was equal to 1 or higher, it would not be integrable. And when we square it, we want it to have trouble.
So less than 0.5?
Yeah. So as long as we're between 1/2, because if we had negative 1/4, when we square that, that's negative 1/2, we can integrate negative 1/2. So as long as we take something like this f is in L1 of 0, 1, but not L2 of 0, 1. Sometimes we put additional square brackets around 0, 1 to be really pedantic. Other times we don't care. So what this tells us is L1 is not a proper subset of L2. L1 of 0, 1 is not a subset of L2 of 0, 1. What could be true? So L1 is not a subset of L2, 0, 1. Maybe L2 of 0, 1 is a subset of L1, 0, 1. You always want to get a sense of how strong of an assumption do you need to make. The if not, worst talk I ever went to a contender was a talk at Princeton about a function f such as like f log squared f is in L2. It was a very technical assumption to lead to a slight improvement in a certain result. And it's, what's the weakest condition we need to make something follow? And when we're trying to make assumptions, is it stronger to assume a function is integrable or square integrable? How many of you have taken physics? Quantum mechanics? Seems good. So in quantum mechanics, we often look at the absolute value, the modulus squared. And the modulus squared often represents the probability. And when we get to quantum mechanics and we get to, we might do the Heisenberg uncertainty principle, it's all a statement about functions and their Fourier transforms. And the modulus squared is related to probabilities. So do you think an L2 function on 0, 1 is always going to be integrable? So here's the question. If the integral from 0 to 1 of f squared is less than 1, is less than infinity, is the integral from 0 to 1 of f less than infinity? Now, we are fortunate in this moment that we are only looking on the interval 0, 1. We don't have to worry about decay rates. So it could be that f is decaying slowly, but when you square it, it's now decaying rapidly enough at infinity to converge. But if we don't square it, there could be an issue. We're on the interval 0, 1. We don't have to worry about what's going on at infinity. We can just localize our study to what's going on at 0, 1. And so let's consider the absolute value of f of x. We know it's at least 0. And we want to compare this to f of x squared. Well, if it was always less than f of x squared, then we would know that the integral of f is less than the integral of f squared. So is the absolute value of f always less than f squared? Okay.
No.
When is it less than f squared?
When is it less? When it's greater than 1.
When it's greater than 1. So if the absolute value of f of x is greater than or equal to 1, then the absolute value of f of x is less than or equal to the absolute value of f squared. So if the value of the function is large, we can bound it by f squared. What should we do when the value of the function is small? Then we could bound it by 1. So if the absolute value of f of x is less than or equal to 1, then f of x is less than or equal to 1. So we know the absolute value of f of x is less than or equal to f of x squared plus 1. Because if the function is greater than 1, it's less than f of x squared. If it's less than or equal to 1, it's less than or equal to 1. Therefore, the integral of f from 0 to 1 is less than or equal to the integral from 0 to 1 of f squared plus the integral from 0 to 1 of 1, which is less than infinity. So we actually can conclude that L2 of 0, 1 is a subset of L1 of 0, 1. The square integrable functions on 0, 1 are also integrable. The other way does not go. It's not a proper equality. Do you think that this proof works if instead of 0, 1 we look at 0, infinity? So what might go wrong if we tried to do this proof on 0, infinity?
The integral from 0 to infinity of 1
Yeah.
is infinite. You can't really subtract that on both sides.
Yep. This is where we're using crucially the fact that we're looking at a finite space from 0 to 1. And because it's a finite space, this is just a constant 1. We could have gone to the interval 0, 5, wouldn't make a difference. but it has to be a finite interval for that to work. Okay. So now we know that assuming a function is L2 is a weaker assumption than assuming it's L1. I'm sorry. Let's see. Okay, I want to make sure I say this. Everything that's in L2 is in L1. So if I tell you you're L1, you're definitely L2. But if I tell you you're L2, you're not necessarily in L1. What did I just do? Did I write things? Did I wrote things the wrong way?
You say it. No.
Wait.
That's right. You just said
Yes. No. Okay.
If you're L2, you're definitely
If you're L2, you're definitely L1. But if you're L1, you're not necessarily L2. Okay, that's the way to go. So if I tell you you're square integrable, you're also integrable. But if I tell you you're integrable, you're not necessarily square integrable. So you have more information if I tell you you're an L2. We know more about the function. And so it's a weaker assumption. Oh, sorry, it's a stronger assumption. It's more restrictive. It's more restrictive as to which functions we are looking at. Okay. Now that we know this, we can now finally define the Fourier coefficients. We're going to be working right now just on 0, 1. Eventually, we will work on negative infinity, infinity. So Fourier coefficients. Let's define f hat of n to be the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx, which is just the inner product of f with the function en. So we're looking essentially at the dot product. And this will be related to trying to decompose our function. And then the goal is to study, I'll call it S infinity of x, which will be the sum, and goes from minus infinity to infinity, of f hat of n e n x. So if you think back to linear algebra, I'm basically finding the projection in each direction and adding them all up and hoping that equals the function. And we have just glossed over so many issues. What's one issue? So what's the one thing we have to worry about when I write this down? Does it converge? What's the next issue?
How quickly does it converge?
So one thing is how quickly does it converge? But what else would we like to know about this convergence? Not how quickly, but to what? And what do you hope it converges to? Yeah, does it converge to f? And so in fact, sometimes people write not just S infinity, but they might write S infinity of f to just remind ourselves that this is the series associated to the function f. And then, what do you mean by converge? Do you mean does it converge pointwise? Do you mean does it converge in the L1 norm, so that if you look at the integral of f minus S infinity, that's small in L1, or maybe small in L2? There's lots of different ways to talk about convergence. Pointwise convergence is the best. And then if you can't have that, maybe I can have something a little bit weaker. So there's a lot of issues here. One of the big questions is, these set of vectors En, are they complete? Do they span all directions? So for instance, if I forgot the negative ones, we would be able to write down very easily some functions where it's not going to work. Or maybe imagine I just write down, I'll just leave it like that. So the big issues are, is this complete? Do you have every direction? And what functions can you represent as a combination like this? So the first thing as a nice exercise is to show that En Em equals delta nm. So this is the Kronecker delta symbol. It's 1 if n equals m and 0 otherwise. So this means that the ENs form an orthonormal basis of a space. They are all mutually perpendicular, and they all have length 1. And we're using the L2 notion for length. So the question then becomes, what space are they a basis for? And so a lot of the work on Fourier series goes back to...
Is it on the unit circle?
So it's either on the unit circle or on the unit interval 0, 1. You can look at it either way. Sometimes people talk about the wrapped interval because you can just go along the circle. So who do you think Fourier series goes back to? If you had to guess. No guesses on who Fourier series go back to? Really? No one has a guess on who Fourier series goes back to?
Like who came up with it?
Yes.
Fourier.
Yes. Have any of you seen Fourier series before? Did you see them like to solve equations in physics? And so the idea was you were trying to understand like heat equations or wave equations, and you would say, well, you know, I understand these sines and cosines, and let me see if I can build up a complicated solution in terms of simpler solutions. And so we have a lot of different properties about these. So, you know, as a nice exercise, you know, go through and do that. So there are 5 properties. So let's see, I'll try to write them over here. So this is lemma 11.2.2. The first one, let's use this in focus, yes, is that f minus Sn En equals 0 if n is less than or equal to n, where Sn of x is the sum, and goes from minus n to n of f hat of n En of x. So what we're doing is we're taking a finite approximation to the infinite series, and we're saying if we subtract off that finite approximation and look and see how much is in the direction of En, the answer is 0, which is what you would expect to do if you're trying to decompose. The next one is f hat of n is less than or equal to the L1 norm of f. Okay, this one is a little bit more work, but not too bad. Well, f hat of n is the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. So when I take absolute values, the absolute value of an integral is less than or equal to the integral of the absolute value. So this is less than or equal to the integral from 0 to 1 of f of x dx, because the absolute value of e to the negative 2 pi I n x is just 1. And this is just the L1 norm of f. So as long as the function has a finite L1 norm, f hat will exist. If the function is in L2, does it have a finite L1 norm? Yes, we just showed that earlier. So if the function is integrable, or if the function is square integrable, that's enough to ensure that this exists. All right. The next one is the first one that's really interesting and important. And this one is going to be that a certain sum is bounded by a norm. So I'm going to assume now that f is in L2. So f is in L2 of 0, 1. Then the sum, n goes from minus n to n, of f hat of n squared is less than or equal to the L2 norm squared. And in fact, if this is true as an immediate corollary, true if we place n with infinity. Because if this is always less than or equal to this, as I take the limit as n goes to infinity, it will still be less than or equal to that. It turns out that something a little bit stronger than less than or equal to holds. It turns out they're actually equal. And this becomes one way to actually calculate an integral. The integral will then just be the sum of the squares of the coefficients. Okay. So, question or? Okay. So proof. The proof uses one of the most important inequalities in all of mathematics. So have any of you been told what the most important inequality in math is? Anybody have any candidates? It's not a bad inequality. You know, it's in the top 10 list. But it's not at that premier spot. It's not at that premier spot. He said the triangle inequality. You know, it's a respectable choice. Even U.S. News and World Report ranking doesn't have that in the top 3. Well, maybe top 3. The most important inequality in mathematics is if you have a real number, its square is non-negative. So if r is real, then r squared is non-negative. It's amazing how many things follow from this observation. So it all comes down to looking at the correct quantity. And so we want to figure out what should we look at. Well, I need something that's squared. An integral, a dot product of a function. Let me look at f minus Sn and dot it with f minus Sn. That has to be greater than or equal to 0. I'm not going to go through this, but if you do the standard algebra basically of inner products and dot products, you will see that this is going to be ff minus snf minus fsn minus sn sn. Okay. The last one should be positive. Thank you. And so now all we have to do is figure out these 3. Well, this is going to be the complex conjugate of this. You know, they're just switching the order. So if I can do one, I can do the other. So let's look at one of them. So let's look at fsn is going to be the integral from 0 to 1 of f of x, and then the sum, and goes from minus n to n, of f hat of n e to the negative 2 pi I n x dx. What do we know about the integral and the sum? What can we do? Yeah, we can switch them. Why can we interchange the integration and the summation? This is where you need your real analysis. This is where you need your multivariable calculus, your real analysis, your applied real analysis. It's a finite sum. And the integrals converge. So basically, the Fubini theorem is if the integral sum of the absolute values is finite, then the integral sum is the sum integral. And you can switch orders. I will try to remember to put a little video of Cam showing you how to switch summations from when he was 2 years old with his magic bubble bond. I did not train him to do what he did. He just was inspired that day. So this is the same as n goes from minus n to n. F hat of n. Oh, and we're going to be very careful. There is a small mistake in this line. Anybody see the small mistake in this line? Yes?
Do you want to write it as e to n of x rather than e to the negative 2 pi?
Well, I mean, this is the complex conjugate of e to the nx. And when I have the dot product of two things, I take the complex conjugate of the second piece. So I should have e, the complex conjugate of e and x, which would be a minus sign here. So what's the mistake? I put the complex conjugate on the e. I did not put it on the f hat. This should be the complex conjugate of f hat. That's how I define my inner product. So I have the complex conjugate of f hat times the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. Oh, but what's this integral? That's just f hat of n. So this is going to just be the sum, n goes from minus n to n of f hat of n squared. When I handle this piece is the complex conjugate of this piece. So, mathematicians are lazy. You've all taken classes with me, you know this by now. Right? I don't want to do similar algebra. I'll just say it follows identically. Or if you want, since this is the complex conjugate, just take the complex conjugate of this. But what kind of number is this?
Professor, how do you take, if f hat n is a function of x, how do you take it out of the integral?
F hat of n is not a function of x. F hat of n is the Fourier transform at n. It's the Fourier coefficient at n.
If you say it's equal to f of x.
No, this whole thing here, this integral, is f hat of n. Right? That's my definition of a Fourier coefficient. So the x dependence is gone. I've integrated it out. So this quantity here is just a constant. We put the f to remind us where the constant comes from. Some people actually use a sub n to just emphasize that it's a constant, but then you forget which function it's coming from. I like the f hat to remind myself it's a function derived from the original function, but only defined at integer values. So this is a real number. So its complex conjugate is itself. So this and this are the same, and it turns out when you do the algebra, this is the same because the exponential functions are mutually orthogonal. So when you do the double sum, the only thing that matters is the diagonal. So as a little bit of algebra, you will see that this piece over here also equals this value. So you have that value twice with minus signs, once with a positive sign, so you end up having it just minus. And then that finishes the proof. So we have 0 is less than equal to f dot f minus the sum of f hat of n squared. So the rest is just putting in the algebra and filling it out. Okay? Is everybody comfortable with the rest of the algebra? Okay. So now we have this wonderful result, and we know the result is even true if we replace n with infinity. So I'll just say that this, and this are all the sum from minus n to n of f hat of n squared. And that's what finishes the proof. All right, so now let's look at a consequence. So we're proving 5 statements. We've got 3 so far. So we showed if f is an L2 of 0, 1, then the sum, and it goes from minus infinity to infinity, of f hat of n squared is less than equal to f dot f, which we can also write as the square of the L2 norm, just so we keep seeing all the different notations. Okay? This allows us to deduce something about f hat of n. What can we deduce? What must be true about the f hat of n's for this infinite sum to be less than equal to a fixed finite number? Because again, we're assuming f is an L2, so this is less than infinity. So the sum converges. So what do we know if the sum converges? What can you deduce if a sum converges?
As n goes to infinity, f hat of n absolute value squared goes to 0.
Excellent. The only way a sum can converge is for the terms to go to 0. Do the terms have to go to 0 if the sum converges? Yes. If the terms go to 0, does the sum have to converge? No. But so now we reduce our fourth thing. F in L2 of 0, 1 implies f hat of n goes to 0 as the absolute value of n goes to infinity. And this is called the Riemann-Lebesgue Lemma. And this over here is called the Bessel inequality. So the way we've done it is the Riemann-Lebesgue lemma is a consequence of the Bessel inequality. But because we're doing it as a consequence of the Bessel inequality, we have to assume that our function is square integrable. It turns out the Riemann-Lebesgue lemma holds an even greater generality. It holds even if the function is just integrable and not square integrable. That's a little bit more work to do. But for what we're doing right now, this is sufficient, and we're able to get convergence. And the convergence then tells us that the only way it can converge is things go term by term to 0. So what I'm going to do is I'm going to just do the last part of lemma 11.2.2 and then talk about some consequences of stuff like this. So one of the things we always want to know is how properties of f affect properties of its transformations. So for instance, if f is continuous, if f is in L1, if f is in L2, if f is differentiable, what do these additional facts tell us about the Fourier coefficients? What do they tell us about the Fourier series that we're trying to build? Not surprisingly, the nicer your function is, the better convergence you get with the Fourier series. And the definition of nice for us is differentiable. The more differentiable you are, the better things are. For a lot of things, once differentiable is enough. For some things, you want twice differentiable. For some things, you want just a little bit more, 3 times differentiable maybe. So the last one is if f is an L2 of 0, 1 and is k times differentiable, then there exists a constant c which depends on f prime, and k, its kth derivative, such that f hat of n in absolute value is less than or equal to, I'll call it maybe c sub k. C sub k divided by n to the k. If n, what do I want to assume about n? Not equal to 0. Right. I don't want to try to show that now, it's still true if n equals 0, it's just useless. So this is really nice. What this is telling us is the more derivatives you have, the better decay you get. So here's the proof. We have f hat of n is the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. And we're assuming f is periodic. And we're assuming f is in L2 of 0, 1. So what do you think I want to do? And I know f is k times differentiable. Okay, but if I differentiate the left, what do I get when I differentiate f hat of n? So what's the derivative of f hat of n? And I'm not even saying with respect to what. I'm just saying, what's the derivative of f hat of n? I claim it doesn't matter what you take the derivative with respect to. What's the derivative of f hat of n? It's 0. It's a constant, right? It doesn't look like a constant. If you want to have fun with a Calc 1 student, I should probably be careful what I'm saying, give them as an exercise, find the derivative of x times the natural log of 5. They will frequently use the product rule and not the constant rule because it's not processing that the log of 5 is just a constant. I want to somehow involve the derivative of f. I can't take the derivative of f hat of n. because this is a constant. The only place I can take a derivative is inside the integral. So how could I take a derivative inside the integral? What could I do?
Differentiate and then integrate.
Okay, so what's that called? It's an integration technique. It's one of the two integration techniques you need to know. You need to know that, and you need to know U substitution. You know, I'm not going to have you do partial fractions. I'm not going to have you do trigonometric substitutions. But you need to know how to do this. So integration by parts. So, you know, let's let U equal something, and let's let dv equal something. The challenge, of course, is what do you want U to be? What do you want dv to be? Well, given that we want to somehow get f prime into the game, what do you think we should have U equal? What should we take for U? F of x. And then du will be f prime of x dx. dv is now e to the negative 2 pi I n x dx. So v, and if you're not comfortable, you can write this as a cosine plus an I sine, or actually cosine minus an I sine, integrate each one individually, and then recombine as an exponential. And what should we get? We should get an e to the negative 2 pi I n x divided by negative 2 pi I n. And so now if I take the derivative of this, the negative 2 pi I n x comes down and cancels that. And we'll get this. So now when we integrate by parts, we get f hat of n is equal to uv at 0, 1 minus the integral from 0 to 1 of v du. But because we assume our function is periodic, what do we know about the integral at the boundary terms? So what will the integral at the boundary terms be?
They're equal.
Yeah, they're equal. So this expression will become 0 as periodic. Okay. Now the negative sign here will reinforce the negative sign there, and we will now have that this equals the integral from 0 to 1, I'll write this way, with a 1 over 2 pi I n outside, f prime of x e to the negative 2 pi I n x dx. If we wanted to do this again, we'd have a 2 pi I n squared, a 2 pi I n cubed, etc., etc., etc. And we'd be left with an integral of fk derivatives. And so now, just putting the pieces together, we end up getting that f hat of n is equal to 1 over 2 pi I n to the k, integral from 0 to 1, the kth derivative of x e to the negative 2 pi I n x dx. And so if I take absolute values, f hat of n in absolute value is less than or equal to the kth derivative, it's L1 norm, divided by 2 pi n to the k. That's my constant. And then here's the 1 over n to the k. So there is the decay. When you want a sum to exist, oh, wait, great, this is great. We're looking at the sum of f hat of n. If f hat of n is decaying like 1 over n squared, the sum's going to converge. So you can see twice differentiable means that your Fourier series will converge pointwise. Great. Once differentiable, not necessarily. So the more you know about how smooth your function is, the more you know about how differentiable it is, the better the Fourier series will be. Just as some notation, we often write f of x is less than equal to g of x, or f of x equals big O g of x. if there exists an x naught and a c such that for all x greater than or equal to x naught, the absolute value of f of x is less than or equal to c times g of x. So the way we're writing it here is we always assume this function g is positive, but you could, of course, I guess, have a similar one where you put in absolute values there. And just talking about, comparing magnitudes. We typically have g be positive. It doesn't say that it has to hold for all x, just from all x from a certain point onward. So for instance, if there was a place where g of x vanished and f of x is not 0 there, no c would work. It's just saying from some point onward, if you go far enough down, everything is fine. And so this is extremely powerful notation. This is called big O notation. We'll often do the double less than. Okay, so I think we have time for just like one last example of just the need to be careful. And so a lot of the subject of Fourier series is there are technicalities as to when you will have convergence. So question, if the L1 norm of f, the L1 norm of f squared, the L1 norm of f to the 2017, all L1 norms are less than infinity, does f of x go to 0 as x goes to infinity? So I'm telling you, the integral of the absolute value of f is finite. The integral of the absolute value of f squared is finite. F cubed is finite. F to the 4th is finite. All the way up to f to the 2017th is finite. Does this mean your function has to go to 0? Or in fact, maybe I don't even need to give you all this extra stuff. Just if I tell you that the L1 norm, and I'm on here now, I live on minus infinity, infinity now. So if your function is integrable, does it have to decay at infinity? Or can your function be integrable and not be decaying?
F of x is equal to 1.
But that's not going to be integrable. That will be infinite. So you want all of these to be less than infinity. So if you took f of x equals 1, then the integral is plus infinity.
Oh, you're integrating from negative infinity.
Negative infinity to infinity. So if you could choose life, if you could choose a mathematical world, you would like to say if my function is integrable, square integrable, cube integrable, blah, 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 it's got to be decaying. So imagine here's n plus 1 over n to the 2019. Here's n minus 1 over n to the 2019. And there's lots of ways I can do this. I'll have it, this is going to be height n. So this is not even remotely drawn to scale. And then I guess just to make things a little bit nicer, I'll put a 2 down here. If you want to make the function continuous, you could do a triangle instead. It doesn't really matter. If you look at the area under this, it's a little bit nicer with the square. Because now it's constantly equal to n. The block has length 1 over n to the 2019. So the area of this rectangle is n over n to the 2019. So the area under f is 1 over n to the 2018. And if I sum this over all these n's, I'm going to get something that's finite. If I looked at the area under f squared, I would now have an n squared over n to the 2019. There'd be a 1 over n to the 2017. Everything would be fine. If I took f to the 2017th power, then that rectangle from n minus 1 over 2n to the 2019 to the n plus 1 over n 2n to the 2019, this would be equal to n to the 2017 over n to the 2019. That's 1 over n squared. It's square summable. So here is a function where all of these are finite, but the function is not going to 0. It's actually going to infinity, but on smaller and smaller sets. And in fact, if I looked at the integral of f to the 2018, it would blow up. So it gets even worse. So the first 2017 powers are all integrable. The 2018 is not. The function is going to 0 almost everywhere, but there is a very small set of measure 0, these are measure theory terms, where the function is blowing up. So the problem is, whenever you have convergence, you can't make deductions about what's going on point-wise. You can make deductions at what's going on in general. So it is really good to think about examples like this. You've taken probability with me before, or similar classes. You've seen e to the negative 1 over x squared. Functions like that, these are the dangers we have to play with. All right, this is a good place to stop for today.